I welcome you all to this problem solving session of the NPTEL course Power Plant Engineering. I am Tanma Sharma and I am the TA of this course. So today we'll learn about the economics of power plant and how to solve the questions related to the economics of power plant. So let us proceed. So first of all, I would like to give you an idea about what kind of things is going on in a power plant in a combined cycle, or even if the cycle is not combined. Okay, so what do we mean actually by combined power plant? So basically, we are mostly focused on how to meet the electrical demands or the power demands of the society, right? So what is a power demand? It is being represented by a load curve. Okay, there are two kinds of curve: load curve and the load duration curve. So a load curve, basically it gives the means monthly or the annually or weekly even the consumption of power. Okay, suppose in the first month, so the consumption of power was this much. Okay, and suddenly the in second month, maybe due to a lot of festivals, a lot of power may have been consumed. Suddenly there was a decrease, again there was an increase. Okay, maybe in the summer, due to the use of ACs and everything, there is a huge power consumption. In winters also, there might be the use of heaters, which uses a lot of power consumption. So based on the, different seasons or different requirements, the power consumption rate will keep on changing with respect to time. So sorry, the power consumption will keep on changing with respect to time. So this is a load curve which shows the power consumption throughout the year, and in year actually it is represented, the x-axis is represented in time, in hours. So it is given till 8760. Why 8760? Because total hours in a year is 365 days into 24 hours in each day. So that is equal to 8760 hours approximately. And the y-axis is in kilowatts, so total amount of power being consumed at a particular instant of time. So now if we arrange this peak power, suppose this is a power, okay, and we see how much time at this power it is being consumed, means if we need to see at this power level, okay, how many days or how many hours we have consumed this amount of power. So that like that, if we represent it in a time wise cumulative curve, then that will be called as a load duration curve. So if we have a peak power in here, so it is basically used only one in a 1 hour, or 0 to 1 hour, between 0 to 1 hour. So we will have this load power at the initial time. Okay, 0 to 1 hour, it is using this peak power. Then as we see at this lower power points, so it will be this amount of power will be utilized for a longer duration of time. So that's why we see that at this level of power, so this much amount of time is being used. Yes, so this amount of power is being used for this much amount of time, right? So like that, if we arrange it in a cumulative way, then we get a load duration curve. So this is basically a load duration curve, where we represent this load curve into how many hours each power is being used annually. So this axis, it is still the unit is hours, and it is being used till 8760, right? So we will have a maximum limit of 8760 hours time here. And so this is the load duration curve. So there is a difference between load curve and load duration curve, and we will be working on with the load duration curve only. This gives us total amount of power being consumed for means for how many time that amount of power is being used. So now based on this, we know that this is the peak power power consumption. Okay, so maybe the plants that we are using, okay, you see that the peak power is being used for a very short duration of time. Okay, so this amount of power is being used for only this short amount of time. Okay, so if we install, suppose we install a power plant, because the primary target is to get the power, means get the demands, meet the demands of the electrical demands or load demands. So if we install a power plant which supplies at peak load, so it will only supply this amount of power for this amount of time only, but the power plant will be supplying that amount of power for the entire year. But we do not need that much amount of power for the entire year, we need some less amount of power also, right? So based on this, the concept of combined power plant comes, which makes this process a little bit efficient. How? So if we design a combined power plant, like hydroelectric power plant and thermal power plant, hydroelectric power plant and a small nuclear power plant or something like that, this gas turbine, diesel cycle. So if we use this kind of combinations, then what we can do is that we install a base load power plant which will be supplying only this much amount of power, and will be supplying this much amount of power for a very long duration of time. As you can see, this is a very long duration of time, and the additional amount of power, okay, that will be met by a peak load plant. So what a peak load plant will do, suppose at this particular time, suppose if you can see here, this at this time, suppose we need a large amount of power, large demand, then suppose the base is around here, the additional amount of power will be quickly supplied by the peak load plant. Okay, when again the demand decreases and goes below the base load plant, this limit, then the peak load plant will be not operational. So we will be manipulating like this. Okay, so for some time the peak load plant will be operational, for some time it is not operational, but the base load plant will be operational at the throughout the whole year. So that way we can save some amount of power, okay, when the demand is less. So that makes the system quite efficient. So that is why the below, that is 1 and 2 that I am showing, the 1 is basically the base load plant, the total energy is being supplied by the base load plant. Okay, so what is a base load plant? A plant which will meet the basic power demand at a constant rate and will not cater to the changing power demands. Is there any doubt? Okay, so base load plant, it will not cater for the changing this power demands. It will supply at a constant rate. Okay, suppose a plant which is having a very bad this parting means at a constant at a particular load it is having a very good efficiency, but at different loads it is having a very bad efficiency. So such kind of plants like this uh, yes, gas turbine power plant. So this kind of or this hydroelectric power plants, so such kind of power plants can be actually used for a base load power plant. So it has a high means durability to supply for a very long amount of time at a constant rate, and that way we can select the base load power plant. And a peak load power plant should be selected such that it can quickly start, quickly switch off, and it can quickly meet to the demands. So that is how a peak load plant can be actually decided upon. Okay, so a peak load plant is a plant which will meet the changing power demands. So this was about the base load plant and the peak load plant and the load duration curve, and based on this whole concept we'll be moving forward and deriving a few equations and then again solving a problem to see how we can actually understand the economics of power plant, how we can be economical in designing a power plant. So let us move on. So here what I am doing is that first of all, economics of power plant means the amount of money. So how much amount of money are we spending for each power plant each year? So is that optimal, or are we spending a little bit more, or are we spending a little bit less? Or the question for answering such kind of questions, like how to decide upon a peak power plant and a peak load power plant or base load power plant, depending upon the different cost factors in each of the power plants. So if the cost is not optimal, so that combination will not work. Actually it will incur some losses, right? So we'll have to understand what kind of things affect a power plant, so or the cost price, annual price of a power plant. So first cost is the fixed cost. Suppose we need a certain amount of land, okay, so then that is incurring to the fixed cost. Then the second cost is cost per capacity of the plant. So per capacity, so if we increase the capacity to deliver power, okay, that means in if for example, if I give you the example in a Rankine cycle. So to increase the capacity, what can we do? First of all, we will increase the capacity of the boiler, okay, so that more amount of steam will be produced. Then we'll have to increase the capacity of the turbine, steam turbine, so that more amount of power can be produced. Again, that would again increasing these sizes will again incur some incremental cost, right? So if we increase the capacity, we are actually increasing the cost per capacity. So this is a particular constant. Okay, suppose we assume that this is a particular constant. As per increasing capacity, we will add this constant. So that is the cost per capacity of the plant. Okay, and the third is the cost per energy generated. So if we see all the losses, if we accurately analyze all the losses which are happening in the power plant, and again from the turbine to the generator, these losses are also happening, then labor cost and everything. Okay, so environmental factors, so everything if we consider together, so per kilowatt hour, per amount of energy, we are actually spending some amount, spending some money. So that cost which is incurring per energy generated is the cost per energy generated. And the energy generated is in kilowatt hour, so I'm mentioning this like this. So we can write basically the total annual cost as A1, which is the fixed cost, B, which is the cost per capacity of the power plant in kilowatt, so into the total capacity of the plant, and plus C, which is the cost per energy generated into the total amount of kilowatt hour or energy generated. So that will give us the total annual cost. Okay, so if we analyze it annually, then yes, it is an annual cost, since we are actually considering 8760 hours together. So that means we are considering 365 days or 1 year. So that is why I am saying that it is an annual cost function. Okay, so so yes, so this is a now we'll analyze the base load plant and the peak load plant differently. Okay, so the cost for each of these will be different. So base load plant is actually I have denoted it with subscript 1, and the peak load plant with the subscript 2, that's A2, B2 and C2. Okay, so like that I have denoted. So now a basic question that comes to our mind is that how can we assure from this formula? Okay, just by looking at this formula, can we really or these two formulas, suppose we have two power plants, we do not know which is the base or the peak, but we need to decide which is the base load plant and the peak load plant. Can we really decide based on the cost functions that are given to us? Suppose we have R1 and R2, we do not know which is the base or the peak load plant. So for that, what we'll see is that the this coefficients of this b1 sorry the constants b1, c1, b2 and c2. So we will compare these two these constants. Now I will give you one thing. So b1 into the capacity it has in the power, right? So for a base load plant, okay, what is happening is that we cannot we are having higher losses if we increase the capacity from a certain level. Okay, actually that is why we cannot increase the capacity beyond a particular level for a base load plant. So that is why for a base load plant the B1 is actually high, because for the same amount of capacity the constant that will be multiplied will should be high, because that is means per capacity we're incurring higher losses. But for a peak load plant, which is a very small plant, if we see, okay, so for a small plant the power per capacity should not be that high. Okay, we should able to go to high peak this powers. Okay, so if we see that if we install the base load plant in this peak power, then we'll have a higher loss in terms of money if we do the same thing for a peak load plant. So that is why the B1 should be actually greater than B2. Okay, to decide upon the base load. That is a disadvantage of a base load plant. That is why we are selecting that plant as a base load plant, because we are not able to increase the capacity to a very high or towards the peak level. Okay, because the B1 is quite high. Okay, then one more thing is that a base load plant should have lower cost per energy generated. So if we see here, the energy generated per this the cost per energy generated, if it is high, then we should be using the peak load plant for everything, right? But actually the base load plant, since it is quite stable, it is not dependent upon much factors if it is in large scale, so that is why the C1 is quite less, okay, for a base load plant. But in the same for peak load plant the C2 is quite high. Suppose if we have C2 a little bit less or even equal, then we can use the all everything in the peak load plant, because the B2 is also less. If the C2 is equal, then we can use it for the everything. But actually that is not the case. For peak load plant, per energy generated the cost is higher. Okay, so that is why the C2 is greater than C1. So this is a condition from which we can actually select what is a base load plant or what is a peak load plant. Okay, the B1 for the base load plant should be higher. Sorry, the actually we should look at alternatively, so the B2 for the peak load plant should be lower than the base load plant, and the C1 for the base load plant should be higher than C2. So we will solve one problem and we will see how it is impacting, and we will have a better understanding at that time. But for now I have just given you the facts. Okay, then so we have the cost functions of each of the base load plant and the peak load plant. So this is the base load plant, and since we are crossing a particular power consumption rate, so this is being fulfilled by the peak load plant. Okay, so we will have to select what should be the capacity of the base load plant till which it will be supplying a constant rate of power, and above which the rest of the power will be fulfilled by the peak load plant. Okay, so that limit, okay, what is the optimal limit so that the total cost by the combination of 1 and 2 is lowest? So that we will have to actually check for. Okay, so suppose we fix a particular power limit. This is suppose this is the base load, okay, and the total time duration for which the base load is working, suppose this is h. Okay, for this much amount at for h time it is h hours it is operational, or we can say that the above this the peak plant will be peak load plant will be operational for h hours. Okay, then if that is the case, so if we somehow increase this h, what effect can we see? So if we increase this by a very small amount kW, so this is power now in the y-axis, so d power. So if we increase this height, so the h this, since this is dkw, the h is almost constant. Okay, the h is not varying, we are not changing the h value. So first of all, the total will calculate the net cost of the combined power plant, so that it will be simply addition of these two, a1 plus a2, then b1 kws bs kwbs. This is different and this is different, so we will add it differently. Then even this cost per energy factor, that is also different for both, so we'll add it differently. So this is the total cost. Now if we increase this limit, okay, then what should be the this effect, let us see. So that will be r2, suppose I am denoting that with r2. So a1 plus a2, this is the fixed cost, so it will remain the constant. Then b1, now since the capacity of the base load plant has increased, so this dkw has been added to the base load. Okay, so b1 into kwbs plus dkw. Okay, so this amount of power has been increased, and again in the peak load power plant this amount has decreased, so we'll subtract that from the previous capacity. Okay, again for cost per energy generated. Okay, so cost per energy generated is given in kilowatt hour, so basically this represents the area within this curve. So kilowatt into time, that is hour, that will give us the area, that is kilowatt hour. So this is the area. And this was the initially this was the area, and this was the area for peak load plant and the base load plant. So we will add this amount of area to the base load plant, so that will be dkw, and since the height this h, the time has not changed much, okay, it is remaining the constant, so this is almost the square. If you look at very minutely, then it will be a square. Alright, so h into dkw, that is the area which is being added to the base load plant and subsequently being subtracted from the peak load plant. So we are adding this to the base load plant, and we are also subtracting this amount from the peak load plant. So this is the total cost per capacity of the combined cycle if we increase the capacity of the base load plant. Okay, now when we have increased the capacity, so we will check how much is the net change. Okay, since we are increasing a very small amount, the change is obviously very small. We can straight away give assume it as 0, negligible change. So we have assume it as 0, r2 minus r1, that is 0. Then if we subtract that, r2 minus r1, so we will get this particular expression, right? All the constant terms will be cancelled from these two. Then on further solving it, we will see that the optimal value or the optimal capacity at which the base load plant should be designed is, so not the capacity for which the peak load plant should be run, is h equals to b1 minus b2 divided by sorry, this is a slight mistake, this should be c2 minus c1. Okay, so b1 minus b2, and since this part is coming this that will be negative, so c2 minus c1. So h equals to b1 minus b2 divided by c2 minus c1. So this amount of this h should be equivalent to this value, such that for this amount of time the peak load plant will be operational throughout annually, and after this the base load plant will be sufficiently giving the power at a constant rate. So that is basically how we derive the optimal duration for the peak load plant, and we will use this particular concept. Okay, we will use this particular concept in further solving the problems. So this was how we derive the h. Then I will give you a basic this formula. Okay, directly I will give you the formula, so of these particular terms. So the installed capacity what should be the installed capacity. So by this installed capacity, meaning for a power plant, the capacity or the maximum capacity at which it can produce the power. Okay, so beyond that it cannot produce the power, but below that, yes, maybe we can, if we control a few parameters, we can produce below that power. Okay, so the installed capacity of a base load plant y1 and peak load plant y2 as shown here. So this is till here we have the power till which it is limiting the base load power plant, and after which if there is a demand fluctuation, then it is being met by the peak load power plant. So if we see that for the peak demand, okay, for the peak demand, so for suppose there is a Durga Puja now, they will come, Durga Puja will be is coming. So at Durga Puja a lot of lights will be this installed, and decorations will be in this process. So it will draw a huge amount of power, right? So maybe that if that is the peak load, so we will observe the power being drawn at around this particular point. So if there are certain power plants, combined power plants, which are actually dedicated to give that amount of power, then the dedicated power plant should be designed such a way that the maximum capacity of the base load power plant and the maximum capacity of the peak load power plant should meet the maximum demand of the society. Okay, so that is the case, and so this is the y2 is the installed capacity of the peak load power plant, and y1 is the installed capacity of the base load power plant. So at the peak power means at the peak demand, the base load and the peak load will be operational at full capacity, right? So the peak load will be giving y2 amount of power, that is the maximum capacity of the peak load, and the base load will be giving y1 amount of power, that is the maximum capacity of the base load power plant. So that is the actually the meaning of the installed capacities of the base load and the peak load. Again, the energy supplied per year. So the energy supplied per year is basically this amount of energy, right? The entire area between the this curve. So that is the total power, this amount of power at each times. If we multiply and add it, so we will get the entire area. So that is basically the energy supplied per area, right? So kilowatt into hour, that is if we convert, we will get in energy units, that is joules or calorie. So this is the energy supplied per year, right? Then plant capacity factor. So plant capacity factor is that the average energy supplied per year divided by the plant capacity. Suppose the plant is having a capacity of like a very high amount in megawatts, then what is the ratio between the average energy supplied throughout the year and the plant capacity? So that is basically the plant capacity factor. So these were few terms, and there are many more other terms, and if you can browse the internet, then you will be able to see a lot of many terms, but these were few of the terms which were actually asked in the assignment questions. So that is why I completely focused on these many parameters only. But yes, you can always explore a little bit more, and you will get a lot many of terms. Okay, so now let us finally solve one problem. Okay, so basically the assignment 8, question number 13 to 15, I cannot directly solve the problem, so I have framed a problem of my own here. And if you are able to understand this problem very well, then I am sure that you will be able to solve all the problems related to the economics of power plant in the assignment. So the question goes as like this: the cost function at both power stations are given. So station A and station B. Is there any doubt? Hello? Am I making sense till now? Is there any doubt? Okay, if there is no doubt, then we can move forward. So in this question, so the cost function of two power stations are given as CA, station A CA is 40,000 plus 100 into the capacity plus 0.05 into the energy produced, and station B CB equals to 20,000, that is the fixed cost, plus B, which is actually a variable not given, and into the capacity of the plant, plus 0.08 into the energy produced. So based and also it is given the maximum load in combined operation is 50,000 kilowatt. So this is the 50,000 kilowatt, and actually here this is the load duration curve that is given, where it is completely a straight line. Okay, so this is completely a straight line. Actually practically it is not possible, but for our convenience we will assume that it is a straight line. Okay, so we need to first identify the base load and the peak load plants. Okay, now for the base load plant, since it will have to operate for a very for throughout the whole year, right? So the total energy produced, the cost per energy produced should be very less, because it will be producing energy for the whole annual year, right? So this is the cost per energy factor. Now peak load plant is only used when it is required to meet the demands, right? So it may have higher, means it will have actually higher energy produced, cost per energy produced. So based on this logic, we can see that the constant that is being multiplied, so 0.05 and 0.08, so this is having lesser cost per energy produced, station A. So accordingly we can say that the A is the base load plant. Accordingly we can say, direct, not even going to this this constants per capacity. Okay, even if we not go in directly to this, we can directly identify that yes, A is the base load plant. Okay, so now we have identified the base load and the peak load plants. Now it is given that as per the data available, the base load plant is operational optimally for only 2000 hours. So actually I think it is it should be peak load plant. So the peak load plant, okay, so this is the peak load plant, so this will be operational for only 2000 hours. So if it is operational for 2000 hours and that is the optimal condition, then we have already derived one particular formula for getting this amount, this h, and h here is 2000 hours, it is directly given. So can we really find out what is this particular constant from that? Okay, so we need to find actually the cost per capacity of the station B in order to proceed further. So for optimum conditions, we have already we know that this is the condition of the time for which the peak load plant will be operational for the in one complete year. So that is 2000, and by solving this we will get 40 rupees per kilowatt. Okay, per kilowatt it is 40 rupees. So this is 40 here, CB in CB cost function, this is 40. Then we will find the installed capacities, right? For installed capacities we need to find YB, which is the maximum capacity of the peak load plant, and YA, so this is the maximum capacity of the base load plant. So since this is a complete triangle, okay, so we can directly assume that YB by 2000, okay, YB by 2000 equals to 50,000 by the entire 8760. So like that YB or Y2, that will be equal to 11,415 kilowatt, right? And so y b, so this part is we have known. So if we subtract this amount from 50,000, we will get ya, so that is 38,584 kilowatt. So this is how we have found out the installed capacities of each of the power plants. Then we need to find the energy supplied per year. So for energy supplied per year, as I have already told you that the area within this particular load distribution curve is the energy supplied per year, right? So since this is a whole triangle, I have directly taken the area of the triangle, right angle triangle, so that it is amounting around 219 into 10 to the power 3 megawatt hour. Okay, so this whole energy is around this much. So now we know the energy supplied per year. After that, we need to calculate the plant capacity factor. Okay, the plant capacity is at 100 megawatt. So if the plant capacity is at 100 megawatt, then so this is actually the average energy supplied per year. So this is supplied per year. Average is basically we'll have to take out the time, this unit out here. So we will directly average it by the entire time, that is 8760 hours, 24 into 365, right, for the entire year. So if we solve this, we will get the plant capacity factor to be 0.25. So basically this was the question which I actually framed on my own, and to help you understand how to solve problems related to economics of power plant. And I hope that now the problem in the assignment will be a little bit more easier. If you just trace the steps, I think you will be able to get the answers. So this was all for today's session. So are there any questions? Hello. Not exactly. Um, it may be because the baseload power plants actually they have very low parting efficiencies. So it is very much efficient when it is operating at the installed capacity. So yes, it should not be deviating much from that. No, no, because yes, suppose start, right? Exactly, exactly. So so these can be used in certain conditions. This may be used as a this peak load plant, and also in certain conditions where there are no other plants having higher capacities. Okay, so these can be treated as this base load plant. So it is actually basically known, the load distribution curve now. So actually it is basically known and referred from the previous years. So based on the previous years, we won't be consuming means a different behavior. The consumption won't be at a different behavior than the previous years. Completely different behavior. We won't be expecting that. So like that, we know what should be the load that should be provided at a particular time of the year. So we will be prepared a little bit beforehand, right? So if this thermal power plant takes a little bit more time, so we'll be now concerned for that amount of time. So we'll be starting the power plant a little bit before the time, right? Right. So are there any more questions? Okay, then if there are no more questions, then this is basically the last session of the this NPTEL course, Power Plant Engineering, and I wish you all the best for the exams, coming exams. So thank you very much. I really enjoyed this experience, and yes, I wish you all the best for your future endeavors. Thank you.